Next, we'll focus our discussion on information visualization. Information visualization can be considered as the process of taking some data that's already in a tabular form into the visual representation. The difficulties here is that the data will usually have large number of attributes. We call it dimensions. When we try to map these higher dimensions to the two-dimensional or three-dimensional space that humans are used to perceive, there is a challenge on the choice of dimensions and how can we represent more than two or three dimensions. There has been a lot of creative ideas on how this can be done. For many of us, information visualization tend to be perceived as a way to present pretty pictures. For example, if you visit Many Eyes, which is a website that has several dozens of information visualization techniques, they're all pretty pictures. However, the goal of information visualization is not just only about showing data in pretty pictures. Visual information should be able to amplify human cognition and should be able to enhance human memory and human visual processing. The other kind of function for visual presentation is that visual presentation of knowledge can be easily shared, and visual language and visual structure are common framework across people and even different language region. Last, information visualization should also consider putting the data into context where people can relate what the observation with the existing data that we already have before. Information visualization doesn't have to be limited to the data you observe. You may also combine the observation with the knowledge that you already have so that you can perceive the data in the context of other data. For example, if somebody asks you to draw a map of your house, you tend to draw your house on the map, but also show the nearby landmarks, the roadways, etc., to make people easier to understand where your house is located. We know that we can perceive graphical information much faster than textual information. However, if I ask you how much faster it could be, you may or may not be able to answer that question. There's many scientific research on human visual systems that are trying to answer that question. So the findings from the cognitive and psychological studies is that human visual perception has a capacity about 1,000,000 times higher than any other perceptual systems. For example, we can only read or hear or smell to take input data in about 100 bits per second, compared to the visual system, which can take input in parallel in about 100 million bits per second. That's a significant difference. We could spend many lectures on human visual systems. It's a very rich area. However, for the interest of time, I would like to just put a few points to highlight major characteristics of human vision system as the input channel. First, human visual systems has the highest bandwidth compared to other input channels. It also has the nature of parallel processing. So we have many sensors in our eye can take input in parallel fashion. Human visual systems also are trained to perform pattern recognition. We are very fast on perceive clusters and outliers and any irregularities. The other points we're going to learn later is that human systems actually have two stages of information processing. Some of the patterns we can pick up very easily without much attention. Other patterns that will need to consume our intentional resources. There's also evidence that humans use the visual memory to think, and to reason. This is one of the important findings and support for information visualization. Let me use an example to show the points I want to make. Here I show the example that you have gone through in your first worksheets. The data sets basically describe the percentage of college degrees and per capita income by states. By looking at this tabular data, we have all the information we need to answer a few questions. Okay, the first question asks, which state has the highest income? Okay, to answer this question, we can just sort the per capita income data from the highest to the lowest, then we can pick up the highest states. Okay? That can be done if we present this information in that fashion. The second question asks, is there any relationship between income and education? This question is a little bit harder with the tabular form because it's asked for trends, for association. Okay? And the third question talk about outliers, and this is even harder to deal with the tabular data. Okay? So let's take a look at how we can answer those questions in the visual or graphical form. Here we have shown the data in the scatter plot form, where the horizontal axis shows the per capita income and the vertical axis showing the percentage of college degrees per states. To answer the first question, which state has the highest income? From the scatter plot, we can easily find that Connecticut becomes the top among the states in terms of per capita income. The scatter plot actually is pretty good at answering questions that concern the connection between two variables. For example, this question asking about if there's any association between income and education. By plotting the states in this two-dimensional scatter plot, we see a strong evidence that the two variables are actually associated in a positive way. For most of these states, the higher the per capita income, the higher the percent of college degrees. So the data actually tells us that there's a When trying to map a data to visual variables, it's not always easy to choose the good mapping because there are so many different kind of variables. Okay, for example, in the data table, usually you can see attributes described as text or numbers. And in terms of what they represent, they can be even more complicated. Some of the numbers represent categories, or numbers may be representing some magnitude of measurements. There's very different meaning. In the field of visual analytics, we tell the difference between four categories of semantic variables. One is categorical data, which normally represent a group of similar things. The second type of data represent magnitude of measurement in terms of numerical values. Sometimes we use intervals, or other cases we use ratio, and these are the numbers that have a high or low, which need to be mapped very differently. And then we have also variables representing locations on the Earth's surface. In this case, we really talk about the coordinates representation of location. Okay? And the last type of data representing those measurements that have a reference to time, and they mostly representing changes, subsequent variations. If we know the type of data we're trying to map, then we can actually start to select the right visual variables for representation. Although there is no fixed rules for doing that, there are certain kind of guidelines. For example, categorical data can be mapped to different shapes, but numerical data is very hard to be represented as shapes. Okay? So in that sense, different visual variables have very different utility in terms of representing the variety of data variables. Okay? Many of these choices remain to be the art rather than science. However, we do have a number of useful rules or conventions we want to follow. In order to provide a guide for choosing the visual variable for different kind of data characteristics, the French scientist Jackie Birding developed this matrix that shows how well the visual variables are matched to different kind of data. So in the table, basically shows all the 9 visual variables can be used to describe quantitative or ordinal or nominal data. However, the preference and choice can be different depending on how accurate you want to depict the numbers. Jack Birding is one of the fundamental guru in information visualization because he was actually the first person articulated such a coherent and reasoned theory for the analysis of quantitative graphical representation. Let's take a closer look at this table. If you look at the top, position has been considered as the top choice for all the 3 kinds of data. Position representation is the first choice for all 3 kinds. This kind of explains why the scatter plot is so important. Scatter plot is the example of using the position in the coordinate system to represent the values and orders and even categories. But if you look at the next choice, it seems to be different depending on the kind of data. For example, to represent the quantitative data, length is preferred over angles over areas. Okay, but if you represent ordinal data, the density is preferred over other kind of color or length. Okay? And if you represent nominal data, actually color becomes the second best choice for representing nominal and categorical data. So that's a very useful guide for visual design. And I hope that you can take this chart whenever you try to design visual representation, compare your choice with this chart. You could find some general guidelines that would be useful. In the field of cartography, people have developed another table that try to guide the choice of visual variable for representing spatial feature. This particular table indicated that geospatial feature can be either points and lines and areas. These are the kind of data characteristics. When you try to choose variables, definitely in this case we cannot choose position because geospatial data has to use the position to represent their location. Shapes and size could be used. However, for representing areas, we cannot change the shape too much. We can only represent area by color value or color intensity and color hue. These are the things we can change, but we cannot do much with shape and size. Okay. On the other hand, point data, they only use the location, the position as the one of the dimensions, but other visual variables were not used. So shapes and size can be used to vary and represent the numerical attributes that come with the point data. You could see that there's a rich choice of visual variable for point data, but for lines and areas, we are pretty much limited to color and texture. Some of the visual design guide we talked about in the last 2 slides has been very cleverly applied to actual design of visualization software. I would like to use an example called tree map to explain the case study how the visual variables can be used to show complex data. Tree map was designed by Professor Ben Schneiderman from University of Maryland in 1991. The principle of this program is to map the hierarchical data into some kind of space filling and space constrained visual hierarchy. The idea is that trees can be considered as nested areas, nested rectangles, and we can use a limited space on the screen to show a large number of hierarchies in depth in a limited space. So I would like you to pause this video for a while and then open up a browser and play with this particular visualization called Map of the Market, which is hosted on Smart Money website. This is a typical use of tree map to show a particular domain. We see that on the left side, the space is filled with rectangles, and they also shown with different color. Areas are divided as regions, which shows the idea of hierarchy from larger regions to subregions, and which shows the different levels of hierarchy. For example, from this particular tree map, we can see certain sectors are doing better than others. Depending on the color that we see, some of the sectors has more green, other sectors are less green and more red. That's easy to compare the performance of multiple sectors in that day. While you are playing with the map of the market visualization, I would like you to answer 3 questions. What does the color represent? What does the size of the rectangle represent? And what do labels represent? And last question, if you have $1 to invest in any one of the sectors or subsectors, where do you want to invest your dollars?